Alrighty, good afternoon, everybody. Welcome back.
Here's the thought.
Thank you.
To Discrete Math. Plan for today is going to do presentations on the Graph Theory 2 packet. Then we are going to take a break and move into talking about Euler paths on a graph. Looking at a little bit of a different definition of graphs, looking at a different definition of paths, and start building towards how can we solve the bridges of Königsberg problem. Office hours. I've got my usual office hour after class. I'm not going to have any official office hours tomorrow because I'll be doing great things. If you're interested in meeting with me later in the week, I will be around Hillsdale and likely able to meet up at some point. Send me an email if you'd like to do that. Or come out Saturday. First, for homework, I was like, I'll perish the thought of giving you homework over the break. Then I realized I do actually want to give you some homework. We'll have another set of presentations on Monday. However, you do not need to do any mistakes journal entries past today. Today is the last one due. So you don't have anything you have to hand in on Monday. Does that help, Lori?
Yes.
Okay. Any questions or comments before we get started for today? Why were the Romans always so good at algebra?
The Romans?
The Romans. It's because whenever they were asked to solve for x, they were always able to solve and get x equals 10.
Nice. X is
10 in Roman numerals. Alrighty, let's take a so, well,
I should actually,
all right, let's go with that. Madeline, you are up first.
That's page 2. Do you guys want me to draw the entire graph or? Alright, so for the first question is to draw the subgraph G of G generated by this. So I got this, and if you go back to the first page, it just says that the subgraph can be found by removing some of the vertices and edges of G so that what's left does not contain any dangling edges that can connect to only one or no vertices. So that is what I got for the first one. Are there any questions or? Cool. And then to draw a subgraph that is not the same subgraph as here, I did V2, 3, and V4, and just got this one, and I just said it was different because it only uses 3 vertices as compared to 4 here, and it has 3 edges. Any questions? Or is that wrong? I wasn't here, so I don't know. Yeah.
I think, though I really am not very clear on this myself, that because it says the subgraph consists of V star, I think you would still have to use the same vertices from V star.
Okay, so you do like a the same ones.
You can define a new V star for this one.
Oh, great. Never
Yeah,
mind.
I wasn't
I'm
sure.
sorry. I'm
Okay.
just being rude.
Oh, Any questions?
That is the subgraph of E star though, right?
Are you saying like, cause it uses
Like if
three
it's,
right here, but it's not up there?
I mean like the new V star you defined, that is the subgraph of E star, right?
Yeah, maybe it's a different one.
So like is it saying, what does the not mean? Does it mean it wants you to
The
graph
not
it
means
incorrectly?
I want you to come up with a subgraph that is not that is not generated by the vertices in there.
Okay.
Is that correct then?
I think that is generated by its set of vertices
Yeah.
because
Oh,
you have all the paths that go between those three vertices from the original graph.
So you'd have to like erase one edge, right? Yeah, like any one. Not a
like
vertex,
that.
but
Oh,
one of the edges.
It's a singular of vertices.
this edge, right?
No, sorry.
Whichever one.
That's
Like the whole line, like an
this whole
edge.
thing.
Yeah.
So it'd just be one.
Well, just one of them.
So confused.
Jacob, would you like to go up and
I
Write
did
down
not
what
mean
you
to.
need.
I did not mean to do this. I'm so sorry.
I think, I don't know.
I didn't know if the not meant not the subgraph or not the early, like the problem before.
I want a subgraph that's not a graph generated by the vertices.
There we go.
Oh, okay.
So like all three vertices are in there, but it's not a subgraph because it doesn't have the edge.
Well, I would say it's a subgraph of the original graph because it can only include vertices and edges that were present in the original graph. But it's not the subgraph generated by the vertices because if the subgraph generated by those vertices, you would need all edges between them that were in the original graph. And this one is lacking an edge between two of those vertices that was in the original graph.
Any other questions? Cool, thank you.
Great, Evan, I gave you two. Have fun.
Glad. On the next page of questions, the first question, a graph and a walk in the graph that is not a path. So I drew the graph here. X, Y, and one Z. So I drew something that I'll walk in the graph from X to Z that is not a path. So I did X, Y, back to X, back to Y, and then finally to Z. I believe, correct me if I'm wrong, I believe this is not a path because it repeats a point, or I guess it repeats 2 points before it gets to Z in this example. All good there? Okay, sweet. And then the second question, I believe we crossed something out. So it said a graph and a walk in the graph that starts and ends at the same vertex X, but that is not a cycle. So I drew the graph here. So X, Y, U, and W for no particular reason. And then the walk that is not a cycle would be X to Y to W to U. Yep, and then back to Y, back to W, back to Y, and then finally back to X. So it goes from X to X, but it is not a cycle because obviously it jumps back around. It hits the same point multiple times. You see 2 Y's in there, 3 Y's in there, 2 W's in there. So that is why it is not a cycle. The walk is not a cycle. Any questions there? All good. Thinking of something, Dr. Gershel?
I'll try to think up a tricky question to
I
hurry
got
off your
you. They're
game.
pretty simple questions, so. All right, well, thank you.
Alright, I'll let you all
No, that's not answered.
not answer any more questions. Have a good day. Please apply through.
Okay, page
5, question 3 asks us to draw a graph with no cycles. So that means that you can't start at one point, go anywhere, and come back to the same point without repeating. So my graph had 4 vertices. X, U, V, and Y, and 3 edges. And this has no cycles because you cannot start at any point and do a walk and arrive back at the same point without repeating. Any questions? Great, thank you.
Alrighty, nice job. Alright, last up, Griffin. A little bit of a spicier question here.
Yeah, I mean, it's pretty crazy. Alright. So the last question asks us to draw a graph whose shortest cycle has a length of 4 and whose longest cycle has a length of 7. So I just started that by doing a graph that would have a walk of 4. And then, so this is our shortest walk, and then we need 4 more options for our walk of 7. Did I do too many? Do I have 1, 2? I really can't count today. Wait. Okay. 1, 2, 3, 4, 5, 6, 7. Yep. There we go. Yeah, so that's it. Did anyone have any different ways of doing this problem?
I was about to ask that.
Great minds think alike. Yeah, Laura?
Well, I did it the same way you did, but I saw other people do it where they start with a box, like with the square to begin with, and then instead of going off of the 2 opposite corners, they went off of 2 adjacent corners and kind of made another shape based off that.
Interesting. So they have this, and then they would go off of these 2 corners?
No.
Or these 2 corners?
Yeah. Those.
Oh, so it'd just be. Oh, so you would get all of the points in the original cycle, and then just an addition instead of here. So I could have 1 less vertex if I did it a different way. Cool.
Did you draw the edges?
Yes.
Yeah. Or
All right. No questions? Cool.
All right. Nice. Yeah, nice job, everybody. Made good work of those. Okay. So with that, pass these out to the third.
Here, I think.
Do you have one?
Okay. I was say I passed one back for you, Adam, in that row. So phone. So. Say what? Okay then. All right. So now we're going to change up our graphs a little bit in order to be able to look at a graph that might correspond to the Brutus of Königsberg. And then from now on, we're going to allow for graphs that have multiple edges between the same 2 vertices. So that's something that wasn't allowed in our original definition of a graph, because in our original graph, like an edge corresponded to a set containing 2 vertices. Now we're allowing to have that occur multiple times. And if you look at this graph is actually is actually sort of a graph theory representation of the bridges of Königsberg. Which, if we draw out, is going to look something like this. Or if you remember, bridges of Königsberg had this sort of 7 bridges in this sort of configuration. And the question of, is it possible to have a path that crosses each bridge exactly once? Can sort of be translated to over here. Does there exist something called an Euler path? An Euler path is a path that takes every edge exactly once. So what we're going to be doing, what y'all are going to be working on today is kind of going to be building up some definitions and some examples related to can you find these sort of Euler paths for if we want to start and end at the same point, an Euler circuit in this new type of graph. And then on Monday's class, we'll be starting to build up the sort of theory that says, if there does exist a path that hits each edge exactly once, what can we say about that corresponding graph? What sort of properties does it have to have in order for that to occur? Everybody's very quiet right now. At least Isabel's grinning, so I know people hear it, I think. I hope. Also, check this out. Here's another example of a graph you're going to be dealing with here. Here's a vertex. Here's an edge. What's so strange about this edge in this graph?
Well, there's one vertex. There aren't 2 vertices.
It starts and ends at the same vertex. Y'all are going to be exploring what happens in these sorts of examples. All right. Oh gosh, I'm not going to stand right there because there's a lot of glare now. How to break up groups. Anybody have an idea for how I should break up groups? All right. Oh, I've got an idea. All right. Think of your favorite Thanksgiving food. Why not?
I don't know.
Well, think of it. Favorite Thanksgiving food. His favorite is turkey. Oh, wow. Slightly surprised. All right, Griffin, keep your hand up. How about some form of potatoes? Me too. Stuffing. Hey. Okay. All right, let's get some stuffers in there together. How about Alan? Who would you like to be in a group with?
I don't care.
Say what?
I don't care.
All right, Madeline's in a group by herself. All right, let's do Madeline, Evan, Adam. Sure, you can do that. We'll do a group of Isabel, Holly, Lori. Sure. Lily, Griffin. Sorry to make you keep your hands up. I wanted to get the stuffingers together. His favorite is some sort of dessert. Okay, let's do, we'll do Griffin, Lily, Sophie. And who's not in a, all right, what's your favorite?
Cranberry sauce.
Cranberry sauce?
Sticky rice. It's not really traditional, but it's kind
Sticky
of
rice?
for my family.
Is that a Louisville Thanksgiving dish? Man, I haven't been home in too long. All right, and then the 3 of you are group. All right, get together with your group and have fun.
Glad we share the same taste.
No, I thought about that.
So the way we must
I was like,
know.
sleep in it.
Yeah.
I was kind of
Oh, no,
like,
just
because
eating.
it's a city.
Oh, there are actual.
I like that idea.
Right, I think that.
You like what idea?
I thought that maybe the way,
You
I
know?
must have saw it, but I don't know. I thought it was
And they were very practical.
ABA, like to show
Why?
Ooh, like two different, that would sort of be like
like a one-way street.
two different one-way streets. Oh gosh, I had my fair share of those over the years, like, oh, if you wanna go this way, you go on this block, but you have to go a block over if you wanna come back the other way.
Yeah.
Oh, I feel that. There's no straight connection from my street to Manning. You have to go like 3 streets up, even though they're like parallel streets.
Oh, yeah, I think I know
Out
what you
by
mean.
the high school.
Yeah, there's a few of those in Hillsdale.
Like the middle school.
And then the don't take a left turn here because we decided to angle all our roads together. This.
I know, how barbaric.
Definition of more.
Should've put us in charge. Could have done some graph theory modeling optimal road structures.
For instance, we can find a closed path. Edge. 7 to B, edge 6 back to B, edge 2 back to A.
Well, would it just because B repeats, so like. But a path?
I was saying if it was a non
Explain my
Or if
name.
it's a path, but if it's
Non-Euclidean
a non,
path.
if it's a non.
So when I say non-Euler graph, I mean the sorts of graphs we were doing in the last couple passages where between two vertices, you could only have a single edge. You can't have,
Well,
you can't have an
before
edge
we
that
would
connects
have
a
had
vertex
to
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 itself.
get back from B to
it's
A,
just-
we would have had to use edge 1 again.
Well,
You'd have to,
You
so in a
you'd have
non-Euler
to-
graph, you would have to
you'd
use the
have
same
to
edge
replace
twice.
that AB.
Man, should have made this packet longer, I think.
So like the straight lines that we were doing last time, that we kind of have these, like when those two go back and forth.
Yeah. Well, they don't, the fact that it's a straight line versus curved line doesn't really matter, but here,
Multiple paths from A to D.
multiple edges from A to B.
Sorry.
Also.
Even in a standard graph, you could always have multiple paths from A to
Strawberry.
B, but here you could have multiple edges connecting the same vertices.
I don't know.
In an Euler graph, also possible for an edge to connect the vertex to excel. Call such edge.
Okay, what?
So these two lines in order to find the degree of a vertex. On the graph, each end adds 1 to the degree except for loops, which add 2 to the degree.
Well, that was not where I thought that was going.
I thought it did backwards. Each end adds 1 to the degree.
Okay, that makes sense.
Is that backwards?
No, I think this is how what it's meant to be.
It adds 2.
Each end adds 1 to the degree. Except for loops, which add 2.
Well, I guess.
Is it loops at 1?
Oh, you could
Each
probably
add,
just
each add 1 to the degree of each of the vertices it connects, I should say. What did I say? In order to find the degree, each edge coming into a vertex adds 1 to the degree of that vertex. It'll also add a degree to to whatever vertex it ends at. And if you have a loop that starts and ends at the same point, we just say that loop adds 2 to the degree of the vertex it goes into. Once for entering it, once for.
I think it's just how
The sum of the degree A,
Yes.
What's the degree? The number of edges.
Yeah, does that connect to a vertex?
I don't know how to describe that, but like it makes sense to me. But like, because I want to say it has 5 paths coming off of it, but like the word path means something.
How about this?
For which?
Five edges that kind of go to it where loops you just have to count twice for.
yeah, even though
Going
it's
in
one
and
edge,
going
it's
out.
still.
Well then,
two
no,
degrees.
because
The
we
vertex.
just showed that with A.
It doesn't matter to the question whether it adds
It might be
2 degrees
hard about
to
this.
2 vertices.
I'm pretty
1 to
confident
2
the answer's
vertices or
yes,
2
that
to a
it's
single
still-
vertex.
yeah, right. It's still added 2.
For looking
Because-
at this formula, if you're summing up the degrees in every
because the other
vertex,
one-
it doesn't matter.
Um,
But it
in
does matter
essence,
for
every
determining
time
what's
you
the
added
degree of a
one
single
edge,
vertex.
all of the degrees in the vertices, all of the degrees, like the sum of all of the degrees of all of the vertices adds two more. If you're to do like an edge
Your
from
brain's not
a
here.
vertex to a vertex, that's adding one edge and adding 2 degrees.
Wait,
But if you're adding more and every time your brain lifts, you're still adding 2 degrees to the entire graph, then you're still only adding 1 edge.
A, degree of A
So, like-
is fine. Degree of B,
Because the degree is dependent on the number of edges, not the number of roots.
Right, but if we have the
Degree
two, we have the
C.
two vertices, A and D.
so then that would be
Okay,
18.
so suppose you're connecting a line between A and D.
That's 2 times.
You're
times
adding
number
1
of
degree to
edges.
this vertex
How
and
about
adding 1 degree to that vertex.
Does that
So
work in
you're
general?
adding 1
So
edge
it's only a circuit, Euler's
and you're adding 2 degrees, so like you can think of it
Something to
as
think
2
about.
e plus 1 or 2 times e plus 1.
I want to say yes.
Because
I'm gonna say it, because I thought this
and
was
then
only like.
that'll still equal the sum because you.
I feel like it would be wrong, but because you add 2 for like the loop, then it's like, maybe otherwise,
The degree. The degree of A, it kind of goes back. 1, 2, 3, 4, 5, 6,
So
7.
I
That's
writing
no,
out
that's
this
not
path.
really not how you count it. Like so, they're just ask. So this summation
So
is
is
you
it
look at
still a
every
path even?
vertex and all of the
Uh,
vertices, and you count
is it
this one. This
still-
one's gonna be 1, 2, 3, 4, 5, and then you count this one 1, 2, 3,
If, like,
4,
something
5,
How did
and so
you,
then you're at 10, and you just add up all the values from all the vertices.
So like if.
Yeah.
Like in this one.
So I think it does probably, because like, so this is the sum of the degrees of every vertex.
I don't know, I was just like saying.
So
like,
think about, we have like, imagine we have just a line essentially.
Oh, wait,
Like,
we don't
between
count
like
that
A
one.
and B, let's say.
Gotcha.
So.
And then.
I think it's easier to count. I think it's
That
easier to count
that
the
edge
vertex rather than by
twice.
edge. You're counting the
Because an edge is
total of the
representing the
degrees.
degree of A and the
Go by
degree of B.
Then each vertex,
So
say
it's
how
kinda
many does
like
that
the
vertex
next
have,
two,
and then move on to the next. And
So-
Three, but like
so-
vertex
But that
essentially
way,
count
we
twice the sum.
count this
Well, this one is only
Here,
connected
I'll-
to one vertex.
I think that's gonna count
A
once
loop is
for
only
the
connected
degree,
to one vertex.
to the degree of D and once to the
So,
degree of A.
you know, it will only be
So-
reflected.
So it would
in
be
the
counted
degree of
twice
that
in the
vertex.
total sum
By
of
counting
the
it twice, we
degrees.
essentially preserve that property, so that the sum of the
Yeah, no, I see that they
degrees
both
will
have
still be
line.
an even.
So
So
it's
it's
A, B, C, D. The entire graph is 5, 1, 2, 3, 4, 5.
to use all of them.
5. Did we decide D was 5? C. 1, 2, 3. Oh wait, actually A without the loop is just 3. So that's gonna
And
16.
D also, without the loop.
No, we're counting this loop here.
Oh, we are counting.
Yeah, I'm just without loop
A, but
B,
A is not 10. What if you start on weird?
just for so the degree of this, the sum of all of the degrees in this graph is gonna be 16. And if we decide to count the loop, all we're doing is A, B, C, D,
So it's-
5.
no, you're right.
5,
No, you're right. You're right.
It's a walk.
It's gonna go 18 total, so the sum of
yeah, we
all
can
of
do
the
a
degrees of
path.
all of the vertices
Yeah,
is
it's
gonna be
a-
18.
For
We
certain.
only
So-
added one edge.
It's a walk.
It's
It's a walk.
But
path.
we added
like-
two vertices.
Well, I wanted to kind of have one
So-
way for like the
so-
examples of
at
the
start
C
at A
for
and
that,
then
and
C.
then and then the next day will be like
1,
Euler
2,
circuit,
3, 4,
or
5,
Euler,
6,
what I call
7,
it,
8.
path 2 will have
And in
some
this case, if we're
theorems.
counting this, we have 1, 2, 3, 4, 5, 6,
How-
7, 8,
Dr.
and 9.
That's when you can't finish it, right?
So it's
And
still
everybody
equal
said
to-
Go ahead.
I'll be back in just a second.
Like, yeah, there's a circuit.
Yeah, they're.
What's up?
You call this an Euler path, and here you call it an Euler walk. Is there a difference?
Yeah,
Oh.
every added edge is gonna
No.
add 2 vertices no matter what you do.
Replace walk here with path.
I'm convinced.
Sorry, I'm sorry, when I say an Euler path versus an Euler walk, when I say an Euler walk is a walk that goes through every edge exactly once, replace that with path. It's on,
Yeah. Okay.
this page.
Thank
Sorry, that was a typo.
Ooh.
Need to get my walks and paths straight. Yes, Ruby. Wait, you can answer your own.
Wait, what did you, what fraction did you say?
This should say Euler path.
This is path?
Yeah, I think that's why I did the typo. I'm like, oh, it's a lock that does lock. This is good. It must be a lock.
I don't think so.
Oh God, no.
I think it would have to be a path. Well, to begin with, it wouldn't matter which one you start on, because they all have the exact same, no matter which one.
Yeah. So vertices don't matter, right?
Correct. Well, if you go through every edge, you're going to have to go through every vertex.
I don't even think.
Right, but you'll have to go through them more than once.
Sure. Potentially based on the graph.
Something
Yeah, I
like
think
this
you're right.
would.
Yeah, it's on you.
Wait, hold on. Oh, oops.
Well, we didn't get back to. So a path doesn't, oh, a certain cycle has to get back there, we don't have to get back.
They're all tubes, let's see.
Okay.
Wait a minute.
How long does this take to put into the computer?
Longer than I care to admit.
Like that exercise.
Who do I want? Actually, Laura, you asked, so I'll make it you. You are in charge of sending me an email to remind me to send you all the code for this packet, so you have a way so you know how to make curvy graphs and graphs with loops and stuff.
That's a lot of responsibility.
I think you can do this one actually. Sorry.
It's a lot of responsibility, but Griffin thinks you can do it.
Griffin, would you toss me my agenda?
I think it's even numbers.
I think so.
For Wheeler Survey.
Yes. And then even an odd for paths, and then if it's all odd, there's no path or circuit.
Granted, this is
That's my
a
hypothesis.
vast generalization based on 4 examples.
Yeah.
Does it fit with the examples? Does it fit with this example?
I don't know. I'm
I've
really
finished this one.
the last one's really fun.
Oh, wow.
Yeah, it does.
No.
See if you can refine your answer for when it will have a path but not a circle. There's a path but not another circle. I think you might be close though.
It does. What did you say about this one?
Might try constructing a couple more examples to see if it fits.
Yeah.
I guess Laura, to answer your question from earlier, it's a bit obnoxious yes, it takes a while to put these in like tech, but you also just end up doing a lot of copy and paste. It ends up mostly just once you know how to do the basic stuff, like it basically just ends up being tedious. Like, all right, I need to change this so that E1 so that E1 is above the line here and E3 is below it here, so it doesn't become messy and hard to read.
So this is.
There's a lot of that ends up happening. It's
Fine.
trying to orient the names of the edges and vertices and places that are convenient.
It's like trying to type a resume and everything just goes in the wrong spot.
Basically, it's
Okay, I gotta construct more examples to refine my theory.
darn too.
So these both have a escape path.
Yeah.
Oh, does it have to first circle?
Well, first of all, see if you can find a circuit. If you can't find a circuit, see if you can find a path
Which
at
one are
least.
we asking?
I can find a path.
I'm pretty confident that the second one
Let's
does
see.
not have a circuit.
Yeah, I thought it was.
Oh.
B is a degree of 5. C is a degree of 3. So much counting.
Oh my goodness gracious.
This last one.
1, 2, 3.
I mean, I don't think it is possible, but
I'll bet that.
Yeah, I don't either.
There's no path. At least not as it's been.
I should have
I didn't find any.
So it doesn't suggest the path quite so easily.
I just
70 and 10.
But it like was more like I just like
Oh, wait.
started.
Oh, no, you couldn't. You couldn't do 1, 2, 3, 4, 7, 8, 9,
every
5, 7, 8, 9, 10. You have to do 1, 2, 3, 4, 5, 6.
Yeah, I think a circuit is just a path.
7,
That
10.
Yeah, sorry, what was that Dr. Good?
Dr. Gerstle doesn't understand how. You know, sculpting away.
So it should be 20.
Yeah, I don't think it has to be even. But then it'd be a circuit, yes. Did you not find it?
I think your hypothesis is correct.
Oh.
Lily's hypothesis, whoever's hypothesis it was.
You've thrown doubt on our hypothesis for.
Oh, is that?
Oh.
That's what
Well,
was
this
her?
is like,
Well, that's what I thought.
the kite one.
To cover all of them?
Well, I mean,
Well, because, so this one,
so I agree.
B and D are even, A and C have.
Okay, this one's not.
Is it, do you think it's based on like?
You go like down
That's
over,
totally
Okay, so A, so your degrees are
I
3,
just
2,
yeah,
3,
it was like
3,
just a circle and then I did
C,
a
and
box.
2.
That was a,
oh, yeah, that works too.
Okay,
Yeah, because I.
I
it's
can
the
say
middle
looking
one.
at this,
I looked at
that
that.
I know there will be no
Oh,
paths
To
to
get to
circuits
the
just from
middle
your
one.
degrees.
Or like just either of the ones, like if you do have.
here.
No, yeah, I agree.
Yeah, like whatever one, if you're like trying to.
There did exist at one.
I can tell looking at 2, 3, I can tell from looking at 3, 2, 3, there will be a path that not
Oh, you messed it up.
in a way that 3, 2, 3, 3, 2, 3 has even.
But
This is also, this one's also D.
Just not the adjective.
Okay.
Maybe it's like at least
How can you tell?
maybe it's that at least
No,
half.
Well, where's the fun in that?
Like degree of each vertex.
So at least half. Are you investigating just paths?
Okay.
Just circuits?
Try making a couple more.
Well, circuits, we've already discovered that it has to be. How long does it
So what have we,
accept all of the degrees?
that will turn out to be.
What if we had like a box where the top had two that were connecting it? So you would have 2 3s and 2 2s still, but it would be in a different
Where?
relation. So say instead of having that middle thing, we just had like a loop at the top. Because then we'd still have the same number of vertices, or the same number of degrees on our vertices, but it would be.
I'll have fun back here.
Trying to figure it out.
Like this?
Yeah.
These are a little bit tricky.
Yeah, because I think that might cause some relation.
You what?
I like that.
Because it still has
Yeah.
5 edges.
You figure out what all the degrees are, see if you can find a pattern for, because it turns out if you know the degrees of each vertex, that's enough to tell you whether or not there's going to be a circuit and or a
Every
path.
case,
So what are we exactly?
the cases where half of all you are even.
The circuits, and if
Even
they're
at
all
odds.
odds,
All have
all odds, there's nothing. Circuit one path.
And then what's the condition for having a path but not a circuit?
Is it half of the
Well, this
vertices
one
have
has
an even
paths, right? And half of them are even.
Yeah.
And but not, but less.
Although I can see why you would concede that from the examples
I
that you've
wasn't
done.
sure if that held, I guess, I just thought that would be most
Try making a couple graphs of your own. See what happens. It's I'll tell you this, it's not half even, half odd for path but not circuit.
You could say that if every.
At least half.
No.
Combination of happening.
So the even and oddness matters though. The proportion.
Well, if you wanna show it that you just need at least one,
I don't know, like, I wish
I don't know how to answer that.
Good
Well, it'd be very
I don't know how to
simple.
answer that. Let me put it this way. Yes for whether or not there's.
I think the next thing to do was try to draw a graph that has all, that vertex is
no
not degrees
for
of
oil.
one and even.
Is
See
it
what
like
happens,
just
and you
some
conclude that if there's at least one
is even,
vertex.
but no,
within
because
one-
some of them
maybe
was
just-
just, some of this one is also
yeah.
one, right?
12
But
is a bad
but
number.
some is even, but some of it individual was
No.
That's, oh wait.
related,
what the
but not
heck? Wait a second.
Okay.
related,
Okay,
but
I counted 12 here,
9-hour drive.
and I counted 12 here.
Yeah.
How is the, how long?
One works and the other doesn't.
That's Zeus.
Everybody says it's because it's even.
What
Even
if
numbers.
it's, what if it's like greater than?
But Euler
There's
circuit
like
did-
the
Vertices themselves.
Have even.
the number of
Okay, because yeah, there's
vertices.
threes in here. Okay,
Yeah,
okay.
it might be the number of
It's nice
vertices
because I have a
and-
Yeah, I didn't come up with that. I just heard everybody saying it.
Well, but
I'm just-
what about
Does it have
the,
something to do with the number of vertices?
oh, because I mean, even if you have just one little baby loop,
No.
These are not confident answers you're
you
giving
still
me.
have
Well, I feel like
a degree of 2.
I'm trying to decide. Well, it's like it's not entirely. So the answer is it's not entirely unrelated. But if I tell you yes, I think it's going to lead you down the wrong
Okay,
path.
okay.
Haha.
Okay, well,
What if it's,
It wasn't even intentional. I was realizing.
I did like some clear work earlier this year, and I don't remember exactly how we solved it.
Was to accidentally say those sorts of
I feel
things?
like it's having a way both
That takes great
and
practice.
off of.
Takes
every
coincidence.
How's your grade?
What's it?
It's good.
yeah,
Math and not
because
a
when it's
circuit,
degree
as long as
3,
there's at least one and at least.
if it's a
at
degree
least
2,
one
you
even and at
can
least
get
one
to it
odd
and away
degree.
from it, but if it's 3, you
Nope.
can get to it, away from it. Wait a second.
Let's maybe build off of this one.
Yeah, but you can't
Like,
start.
what if we just added another
Right, so
vertex?
Wait. If you don't start on A though, that does look a little bit feasible, that you could have a point. Sorry, I'm like, I thought it might
Degree
have 3,
three.
but it's 1.
Oh, yeah.
And it's still could have been just a degree.
Which actually you should work on, but.
what were you about to say, Shafin?
Maybe you only need one.
No, maybe that was it. Like none of them could be odd because
Each will have 3, right? There still exists like the close.
It's
if
a
you're
pretty
not
simple
starting
example to
on
think
it,
about.
So, oh,
you'll get
so here
stuck
we
on
have
it.
2 vertices and 1 edge.
But you can't, well.
That's not a path.
What are we
Each
trying-
what has a
trying to
degree of
figure
one?
out? Rule for half.
Each
That's
vertex
correct.
has
So, sorry, what were you saying? You had to correct some grammar.
We're trying to find the rule for a path now, not a circuit.
Oh.
Because a circuit is every vertex must have each degree. So now we're trying to find the rule for path.
I mean, well, you have a path calculus that if every vertex has an odd number of degrees, it will have
If every vertex has an odd number of degrees, it will have neither.
either a circuit or.
Not necessarily, because that would be a contradiction to that, what you just said.
Yeah, they do.
If you have.
I will say this, in most cases, that ends up being true.
Wait, so it doesn't have to have an even degree?
To have what?
Circuit?
Circuit you do. I think every group's pretty much figured out by now that to have an Euler circuit, it just comes down to every vertex has each degree. But for the minimal condition to have an Euler path is a little trickier.
Okay, so think of something like a tree that does not have an Euler path. So how does it measure? You measure like the number of branches?
Well, all of the endpoints.
You say like by having the given amount of odd degrees.
We'll have an
average.
So there can't be more than one that has a degree. That's a rule. Because if you have more than one, wait a second, that's. Rats. Can't have more than 2. In all reality.
yes, because if we were to add a C, then there would still only be 2 with
You
1.
can do it that way, but you can't. There's a pattern here though. So you start, you go 1, 2, 3, 4, 5.
Right.
Oh,
Wait, that was 1, wasn't it?
So supposing you had a graph like this. This one's not a path. This one's not a path. And you have 3 vertices each with degree 1. Anytime that you have that, you're not gonna have a path. I don't know if that's like the hard and fast rule, but it's at least one of them.
I
Find the box.
Maybe if it's even vertices, it has to have an out of it for objects.
Yeah, that's exactly what I
Just copy it.
Because look, like what has to do Or wait, no, this makes sense. Because
Well, let's look at. Oh,
It's this one.
or maybe for just the circuit or just the path.
Yeah, someone. That was a very, oh, I figured it out, and then a lot of silence.
It's like the like total.
That might be onto something.
No, that was wrong.
I stopped paying attention to you. Guess what?
Does it matter if it's like 4 pages?
I was gonna, like every
Does that have any?
every vertex
I can do this one.
odd number,
No.
an even number of vertices with
some
odd
hesitation.
number of degrees.
There's a lot of hesitation I have to
I mean,
take, like,
that is like
because I have
been
to
the case
think,
in the
like, is that
example once
somehow
too,
equivalent
where
to what
like
I have in mind?
three and then
Oh, so for every
Are you gonna?
I don't
That's
know.
not it. Oh, sorry.
I mean, it seems like that kind of happens, but does it really affect any rules?
Okay, let's do some with loops.
I don't know.
Maybe
But like on this one, there are 2 with 3, and then the rest are even. No, I think you need like just.
Okay. Someone.
And if we erase.
Do you guys have any other graphs that like, I'm just kind of drawing random graphs.
Why?
Anything will fit it.
That doesn't change anything though, because it added 2, so they're still odd and even as they would have been.
There's 5 edges.
Oh, that's an interesting thought.
What is? I'm ready for somebody to just.
The fact that adding any number of loops to your graph doesn't really affect anything, whether it has a path or
There's
you
always
circuit.
an
Yeah.
even amount of.
Oh, dang it. So the whole like, what I said about,
There's always an even amount.
so like, about having to have all of
like that one.
your vertices.
True,
Where the heck did
but
that go?
No,
So having more than 2 vertices with degree 1 is a
for
problem.
instance,
But
all
also,
of
if
these,
these vertices had
for
loops on
instance, all
them,
of these,
there would still be
that is
problems.
an even number of odd degrees.
It sounded good with 7. I thought you were right.
There's no rules.
That is an even number of odd degrees.
Are we supposed to find them?
So frustrating.
Talk about rules
So, I will say this, like,
economics
along the right.
and in order.
Yeah.
Like the same.
Everyone has to know it.
Is there a path in this one?
Sure,
Not that I
so like,
can
like
A
this
path?
one?
Yes.
Oh, because you have to. because you have to go over the same one twice.
Wait.
I think you do have to go over the same one twice.
Balance it out, I guess.
Like this,
Oh, shoot.
I think
I
that
actually wrote
sort
down
of
that there
complicated
was.
example on the board would break that it has,
At the end of the day,
um,
I still agree. Like this one. Idea about.
it has 5 degrees in total, so you can't have the same number of
added
as
to it,
odd.
there's like something.
That's not a necessary condition to have a,
I meant just the degrees here.
Well,
The degrees, they're not on it.
Well, this is
Half of your said that was.
but don't get too caught up on like the shape of it because you could just as easily have like a loop outside that's round from A to D. You know.
That's true.
But I guess.
Any,
no.
Parting bits of wisdom for us?
do I have any parting bits of wisdom
No, what's the answer?
Maybe.
for having a path but not a circuit?
That is the question.
You're right to be thinking along the lines of even and odd.
So even in a what? Degrees?
Degrees, vertex degrees. That is, the the number of degrees of even slash, the number of vertices of even slash odd degree relevant somehow. That's my parting bit of wisdom.
More even than odd.
Wait, are we talking about like, but what about path versus not a path? What about that?
I don't know.
You have to have more even
Have a
degrees
lovely
than odd
Thanksgiving.
degrees of vertices.
You too. Don't spend your time.
Yeah, I think.
Just having fun up here, drawing, like,
Currently, my
things
best
just
guess
grab
is
more and
that
more
even
complicated.
number
Never
of
is-
vertices, that even number can't be equal to the
More even than odd.
like, you can't have all of them have.
It's not, it,
That's my best guess, I don't think it's right.
I'm having trouble coming up with hints now that don't get me.
That's okay.
Every graph, there's something specific that every graph with an Euler path but no Euler circuit has in common. And it's more specific than like, oh, they have to have an even number of something or an odd number of something.
But I think that probably something
A path and a circle have an odd.
No.
That all graphs that have Euler paths but not circuits.
Break is basically here.
There's something interesting with like this graph, this graph, this
I would be going
graph.
home right now.
The distinction between
Yeah,
paths
bowl
and no
game.
paths? That's what you're
Does it have a bowl game?
Yes, there is. Well, no path just ends up being,
I didn't know they
there
did
is no
bowl
Euler
games.
circuit and no Euler path, it doesn't fulfill either of those.
I actually had no idea, I don't know why.
So where's yours at?
Sort of a
It's in,
by process
it's
of
actually pretty
elimination.
close, it's in Indiana.
Oh,
So